Hi friends, welcome to our channel. Let's have a look at a newly appeared problem. Problem 3656. Determine if a simple graph exists. So in this problem, there are given integer arrays called degree. So we want to see if there is a graph with this conditions with exactly these vertices degrees given by the problem statement. So here are two examples. For the first example, the return is true. Now for the second one, the output is false. So here actually this problem I would say it's a bit of graph theory problem. So this is the theory, Erdos Gallai Theorem. So basically we want to check the condition of this theorem, right? So this checking this condition is not trivial, because this here k is the number of the length of the degrees given in the problem, right? So here is partial sum, and this is the fixed number. This is another part of sum, but this part you cannot just compute directly, right? That will not pass the problem statement due to the constraint, because the degrees length can be as long as 10 to the power 5. So the problem here is how to effectively compute this partial sums. This is very easy. You can use prefix sum or partial sums. Well, for this one, you need to also, by way of partial sum, and also I'm going to use binary search here. So notice that we need to sort this D1, D2, so in a decreasing order. But the interpretation of the theorem says that the first largest degrees, k, right, k degrees, is less than this constant, because k is mass fixed is constant. And also, this is the remaining part, the smaller part of di's. Even we compute the smaller ones with compared with k. But because we can sort k, right, once we find the index for which we separate d, I, and the k, then on one side it will be less than or equal to d. On the other hand, it will be greater than d. For those smaller than k, we just sum these di's. For those di's which greater than k, we just count how many k's, which forms the second part in the right hand side, right? So another thing to notice is that the summation of these di's should be even, right? So now let's look at this coding part. So here, let me write something. So here, so we are going to use prefix sum, or you can see partial sum, right? So another ingredient is sorting, right? So we need the degrees to be sorted in decreasing order. But because I'm going to use binary search, I want to sort it in ascending order, right? But you just need to understand the meaning of this mathematical formula. Then no matter you do reverse sorting or sorting from large to small, you can actually adapt, right? Another one is bisect, right, or binary search. So this is for convenience, for efficiency in computing is the right hand side in the theorem. So first, let's get the length of the degree, right? Degrees, and then I'm going to sort degrees. Degrees, I'm going to sort in a decreasing order, in increasing order, right? You just need to count the first key terms from the back, right? So then I'm going to compute the prefix, right? So this actually should be suffix if we sort from increase, but let's just use prefix degrees. Make a copy, right? Then I'm going to populate to this list. So for I in range, so the last term is index n-1 is fixed, right? So n-2, and then ending at 0. So we write -1 here because it ends before -1. So the prefix I will increment, it will be added by this I plus 1, right? So here you can print out this degrees, see degrees, and the prefix, right? So for the first example, after sort, you get 1, 2, 2, 3, right? Then if you do suffix, so that's 3 and 5, 7, and total 8, right? So, but here I'm going to use the prefix because this is easier for us to interpret. But the naming is not essential as long as you understand the essence. So first, I want to see if the summation of the degrees is an even number. So the summation will be prefix 0, right? So if this modulo 2 is not 0, it means it's an odd number. So we need to return false, right? So this is from the based on this Erdos theorem, right? So now we want to check the other conditions. Check the Erdos Gallai inequalities, inequality constraint. So here we need to consider the case in range, say from 1 to n, right? So we write from 1 to n plus 1. So if we consider key terms, so the left hand side will be prefix negative key, right? For example, you see you can print out this. See k equals, and what's the left hand side, right? If k equals 1, so what you are considering is 1, 2, 2, this 3, right? So you can also, so with the print, let's print the degrees and the prefix as might be better, right? So if k equals 1, so it's just a 3. If k equals 2 terms, the sum is 5. 3 terms, it's 7. And the 4 terms will be 8, right? So everything's right. So now, once we get the left-hand side, we also compute the right-hand side. The right-hand side contains 2 terms. So this term is rather easy to compute, just the k minus times k minus 1. The sin is this part. So what we are going to do is the right-hand side. So we're going to set it to be k minus 1. And then we are going to increment with the second part, right? So let's first find the index. So it's the bisect, see left. So degrees, right? And the key. So notice that to the left of this, there's an IDX terms, which is less than this key, right? Because it's less than this key, we just need to do the summation, right? So here, let me consider different cases. First, IDX is 0. It means that every element in the degrees is smaller than k. In this case, so this term is just the remaining summations of di's, right? Exclude this first d terms. So it will be the right hand side incremented by prefix 0. Then we have exclude key terms. So we're going to do prefix negative key, right? So negative key, this number represents the summation of k largest di's. So you use the summation minus those key terms, you get the n minus k terms, right? So this is the one thing. Another thing is IDX. We compare with the because in the left, so we have n minus k terms left. So if this guy is greater than or equal to n minus k, right? In other words, the n minus k terms we are going to consider are all less than k, right? So if this was the case, again, we are going to do prefix 0 minus prefix negative k, right? So the other case is this, actually, IDX is less than n minus k, right? So in other words, among those n minus k terms, IDX terms is less than k, and the other, so let me write down this, idx terms of di are all less than k. So n minus k minus idx terms, so are greater than or equal to k. In this case, we need to, for the first idx terms, so we are going to use the summation of those decays. So it's going to be prefix 0. So minus, because this number, so it's going to be minus, say, prefix idx, because this prefix 0 minus prefix idx, all right, so then the term remains will be terms from 0 to idx, so this sum actually contains the summations of the first from 0 to idx minus 1. So in other words, idx terms, right? So those are the di's that are smaller than k. So the other n minus k minus idx terms is greater than or equal to k. In this case, we should choose k in here, right? So we just write as k, and then we just need to compare, right? If left hand side is greater than right hand side, so we should return false, and otherwise we just need to return true after we exit this for block. So let me do a quick test. Yeah, it passes the 3 cases. Let me comment out these print operations and submit that. If you do not comment out the print operations, it's possible that you get output limit issue. So here another print. Let me submit. And it passes all the cases. So here actually I want to make because here less than or equal to and equal, if the di is equals to k, no matter what you choose, di or k, the same. Therefore here you can use both bisect left or bisect right, and there's no real effects. So I'm going to confine to left. So for each of the problems, you can actually print out the left hand side and the right hand side. So here, say print left hand side and right hand side, and this also let's print out key. So you will see, right? This is 3 less than 5, 5 less than or equal to 5, 7 less than or equal to 8, less than 12, right? So here, left hand side is greater than 4, so we return false. So this one, because the summation is odd, right? So I guess the overall, I would say this problem is not a pure coding problem. So it's a graph theoretical problem. But if you do not know this Erdos theorem, it's not easy to solve this problem. So actually this is by no means trivial. This is the one thing. Another thing is that if we know this theorem, and then checking the condition is also non-trivial. The thing here is how to make efficient computation or check. So here, if you see what we used sorting, and we used prefix or suffix sum or partial sum, and also we used binary search to accelerate the process. So with that said, I guess that's basically about it for the current problem. Thank you for watching.